Good day, everyone. Today, we're discussing thermodynamics, focusing on equilibrium and thermodynamic states. This presentation by Group 7 will cover fundamental concepts essential for understanding how energy and matter behave in chemical processes. These are the group members. Thermodynamics evolved over centuries, beginning with Boyle's law in 1662, defining gas volume and pressure relationships. In the 1850s, Clausius and Thomson introduced entropy and the laws of thermodynamics, establishing equilibrium as a state of maximum entropy. Later, Gibbs advanced our understanding with thermodynamic potentials, and by the 1990s, quantum thermodynamics explored energy behavior at the quantum level. Equilibrium in thermodynamics is a stable state where properties like temperature and pressure remain constant due to balanced opposing forces. The thermodynamic state of a system is defined by specific measurable properties, such as temperature, pressure, and volume, at any given time. Types of equilibrium include mechanical equilibrium, no net movement due to balanced forces; thermal equilibrium, no heat flow between parts of a system at the same temperature; chemical equilibrium, balanced reaction rates between reactants and products; phase equilibrium, coexisting phases like liquid and vapor without change. Thermodynamic processes include isothermal, constant temperature; isobaric, constant pressure; isochoric, constant volume; and adiabatic, no heat exchange. In thermodynamics, 4 types of equilibrium are key: thermal, mechanical, chemical, and phase. Each balances its own forces, ensuring system stability across energy, pressure, composition, and phase. Examples: thermal equilibrium. A hot cup of coffee cools to room temperature over time. Chemical equilibrium. In the synthesis of ammonia, the reaction stabilizes when production equals decomposition rates. Mechanical equilibrium. A book on a table stays at rest due to balanced forces. Phase equilibrium. Water, in a closed container, reaches a balance between liquid and vapor. The Zeroth law implies thermal equilibrium between systems. The first law connects heat, work, and internal energy where delta U equals Q minus W. And the second law introduces entropy, showing that spontaneous processes increase entropy. Gibbs free energy, delta G equals delta H minus T delta S, describes spontaneity. Delta G equals 0 indicates equilibrium. The third law states entropy approaches 0 as temperature nears absolute zero, while the ideal gas law relates pressure, volume, and temperature. Consider a mole of ideal gas heated from 300 Kelvin to 400 Kelvin, doubling in volume. Using the ideal gas law, we calculate initial and final pressures and apply the first law to find the change in internal energy. This calculation is done by using MATLAB. By using MATLAB calculations and manual verification, the initial pressure is 249,420 pascals. The final pressure is 166,280 pascals, and the change in internal energy is 2,080 joules. In conclusion, equilibrium and thermodynamic states are fundamental in describing the stability and energy behavior of systems. Understanding these principles helps us analyze energy transformations and predict system behavior in diverse processes.